let's get back to EE2011. I will appreciate you keep the noise level down because I can't speak too loudly. I have a sore throat, so pardon me, not speaking too loudly. Now for the last class test, this is our results. Get both questions correct, 5 of you. One question out of 2 is 36 of you, so today is the majority. The persons who get none of this correct has been emailed him or her already, please see me, and also 4 missing in actions last week. Now, hope that this week people will come, although I see only about less than 30 students over here. Now, okay, this was the last class test. E field is polarized as shown, okay, and is propagating in the z directions. What is the corresponding H field? Alright, basically, this is got to do with only one single equation here. H is equal to 1 over C E cross K. Sorry, K cross E. E H K. K cross E. That's right. K cross E. Okay. Alright, now, so if that's the case, what is how to solve the problem? Okay, E for the first part is equal to 360 pi x minus 480 pi y. Alright, and K is equal to Z because it has only one component, so K is propagating in the Z directions. Alright, so H is equal to 1 over 120 pi over Z cross 360 pi x minus 480 pi y. I think these questions, most of you got it correctly. Alright, so actually 120 pi, this one becomes 3, this one becomes 4. Alright, z cross x is equal to 3y, z cross x is equal to y, and z cross y equal to minus x, minus plus, so it's 4x. So it's 3y plus 4x, so this is 8, this is 1. Alright, so I think most of you got it correctly. Okay, so basically you just make use of that simple equations. You write down E, you write down K, and then H is equal to 1 over zeta K cross E. Okay, so for the second questions, E is only one component. E has only one component, E equal to 360 pi x. But K has two components. K has two components, which is 3y plus 4z. Now remember, we need the unit vector of K and not K itself. So unit vector of K is equal to 3y plus 4z divided by square root 3 squared plus 4 squared, which is equal to 5, of course, which is equal to 0.6y plus 0.8z. Alright? Now, so H is once again equal to 120 pi 0.6y plus 0.8z cross 360 pi x. 120 pi and 360 pi, this one becomes 3. So this is equal to 3 times 0.6 is 1.8. Y cross x. Y cross x is equal to what? Is equal to minus z. Okay, equal to minus z. And z cross x is what? Z cross x is y, so it's equal to 2.4y. first one correct, the second one wrong? I think basically because it's the cross product of x, y, y, z and all these things that confuses you. Alright, remember x, y, z. So remember, it is always x, y, z, x, y, z. So x cross y give you z. Y cross z gives you x. Z cross x give you y. And if it's the other way around, you just put a minus sign. Okay? So this is the last test. And for this week's class test, I have already given you advance warning. Last Tuesday, I also give you advance warning during the in the announcements. All right, I hope that you prepare for it. Okay, never mind. Let's do a. Okay. Now let's do a revisions. What have we done last Friday? Last Tuesday, we didn't have the class on Friday. Last Tuesday, we started off with Maxwell equations. I just done it this morning. Okay, so I'll convert it in PDF. I'll upload it. Okay, we started with the Maxwell equations and we manipulated Maxwell equations. Then we ended up with the so-called Helmholtz equations or the wave equation. Alright, this is our Helmholtz wave equation. And the solutions for the Helmholtz or wave equations in phasor form is equal to this. Now, this thing I put in EJ omega t is because a lot of times we don't write, but it is there. Alright? Okay, this is the phasor form. This is the polarizations. The vector E can be polarizing anywhere. E0 is the magnitude. EJ omega t is the time harmonics. It's understood. EJ phi, this phi is the phase when at t equal to 0 and at the origin. Okay, t equal to 0 at the origin is what the phase. And T minus JKR. K is equal to KXX plus KYY plus KZZ. Okay, in general propagation directions. R is equal to XX plus YY plus ZZ, which is the position vector of an observation point. Alright? And this thing can be converted vice versa into what we call the instantaneous form, which is equal to this. Remember, look at this. Put all these things into the cosine terms. Cosine omega t minus k dot r plus this is the instantaneous form. Alright? So most of the time you are doing, okay, for exam questions, will be converting from here to here, here to here, here to there, then here to there, vice versa. And also find the parameters. Okay, and also find the parameters. Now, H is the same. Okay, whether is the question give you H or give you E, they should take the same form. I say that it can be the same. What I mean is that if you replace this one by H, this one by H, this one by H naught, this one by H, this one by H, this one by H naught, they are exactly the same form. Same form, okay, but E naught and H naught of course cannot be the same, right? Okay, but how to convert E to H, H to E? Same thing, we have H is equal to 1 over zeta E cross K. I K cross E, E H K, K E H. I myself always forget. Okay, H cross K. Okay, you go by these two equations. Okay, you go by these two equations, and you get one, you convert to another. Okay, and the best thing when you do this, don't do it by instantaneous form, do it from the phasor form. Okay, do it from the phasor form because it contains complex number. Phasor form is easier to do. So whenever you have, put them in phasor form, using this formula to convert to H, and then after that use H from phasor to instantaneous form. No problem. Alright. And then what other thing? Then the propagation constant K, of course, is equal to magnitude K and the unit vector K hat. Right? So the magnitude K, I didn't write another equation, but you should know. K is equal to Kx square root of Kx squared plus Ky squared plus Kz squared. Right? That one I don't have to write. Do I have to write that one? K is equal to square root of Kx squared plus Ky squared plus Kz squared. I think not necessary. Everybody knows that. Okay, and K is equal to omega square root of mu epsilon is equal to 2 pi over lambda. I put equations 1. 1a is when mu is equal to mu naught, epsilon equal to epsilon naught. So my K becomes K naught, free space. Okay, no media, no nothing, which is equal to 2 pi epsilon, 2 pi lambda naught. So I call it 1a. Okay, from 1 you can see that omega divided by K, omega divided by K is equal to 1 over square root of mu epsilon, which is equal to velocity. And from here you can see that omega divided by K naught is equal to 1 over square root of mu naught epsilon naught. This is the speed of light in free space, 3 times 10 to the power 8 meters per second. And also you can see that these two relationship is very simply V equal to C over square root of mu r epsilon r. Alright? And we also have this formula V equal to F lambda or C equal to F lambda naught. Therefore, we can say that lambda equal to lambda naught divided by square root of. Right? There's an error here. Okay? Okay, divided by mu r epsilon r. Now, most of the time, the media that you encounter, mu r equal to 1. Okay, so mu r equal to 1, then that's going to be divided by square root of epsilon r. And then one last thing, this zeta here, which is your intrinsic impedance, is equal to square root of mu over epsilon. And for free space, zeta naught equal to 1 over square root of mu naught over epsilon naught, which is 120 pi. So these are the equations that is distilled from the 20 over slides that you have from the chemical chapter. Okay, and with that you should be able to find all the parameters. The question always come out to find this, find that. You get from these 4 equations. No, you get from these 3 equations. These three equations are interlinked. Okay, they are interlinked. Okay, so actually from these 3 equations you can find all the K, W, V, lambda, whatever it is from these 3 equations over here. Okay, this equation is linked to here. It's linked to here. Okay, so you can find E from H and H from E. And once again, for this type of questions come out, normally it's find K, find omega, find whatever, find lambda, find velocity. And after that, you are given an E to find H. So E instantaneous forms, instantaneous form, phasor form, convert here, convert there. Alright? Okay? So I will upload this one. I'll upload this one for you. Now, this is the revision of what last Tuesday. Today is lossy media. Now, what is the difference between lossless media and lossy media? remember, we started off from your Ampere's law. We start off from Ampere's law. Okay, remember, you don't have to copy all these things down. Okay, this thing will say that if I use the Stokes theorem, this one becomes okay. If I use the Stokes theorem, expand it like this. So my Maxwell equation curl of H is equal to JC. Okay, then I said, well, this JC is the conduction current, right? This JC, we use a capacitor example. This JC is a conducting current, and if it's something in space, there is no conduction current out. I need a JD, where JC pass over to JD, and JD. So I have a JD here. Okay, and then I say that JC is equal to sigma E. Sigma E, and JD is equal to del D del T. This is what I say, right? Remember. Okay, now, when we propagation in free space, in lossless media, now, when you have conductivity, that means you have resistivity, because resistivity is equal to 1 over conductivity. So you have resistivity, you have loss, correct or not? So if it's a lossless medium, that means only have this. We don't have this one. If it's a lossless medium, we don't have this one, we only have this one. Okay, we only have this one because this one has conductivity, and conductivity means has resistivity, it has loss. Now, E is equal to epsilon E, right? So it's equal to epsilon E. That's why we say this is equal to epsilon E. And since we say that E has a Ej omega T and d dt, Ej omega T give me J omega Ej omega T, right? This is what we say before. So this thing becomes J omega epsilon E. Okay, this is the Maxwell equations which we started off to manipulate to get the wave equations or the Helmholtz equations. But now, when we want to do lossy medium. So lossy medium, I must now have curl of H plus curl of H equal to sigma E plus del D del T, right? I must have include this one now. It's a lossy. So it is equal to sigma E plus J omega epsilon E, right? I put this one, I put this thing back in here, the same thing, right? Now, so if I factorize, I get J omega out, I get epsilon plus sigma over J omega E. Okay? No shit, right? I just bring the J omega out. Now you compare this form and compare that form. Okay? Looks the same. Looks the same. The only thing is that now here I have epsilon, here I have epsilon plus sigma over J omega. Correct or not? This and this. Right? That's the only difference. So if I define a epsilon C equal to this, then all my solutions here are exactly the same. So lossy media is very simple. The calculation, because it's complex number, okay, calculator computation is very complicated, very complex. But theory, no different. I just replace epsilon. I just replace epsilon here with epsilon C. Okay, I just replace epsilon here with epsilon C. I just replace epsilon here with epsilon C. Okay, and everything else what? Okay, so the solutions is actually very simple, exactly the same. Transition from lossless to lossy is just simply replacing epsilon with this epsilon c, which is this complex number. But because this is a complex number here, when you find k, it's complicated, right? Because complex number, you have square root of complex number. All these things will become troublesome. Alright? That is the only. And because of the complex number, k is complex. When k is complex, what does it mean? When k is complex, k becomes something like this, d minus j alpha. K becomes a complex number, and what does it mean? Let's take a very simple example, e minus jkz as an example. Alright? So now it becomes e minus j beta minus j alpha z is equal to e minus j beta z e minus alpha z. Am I correct? Minus and minus cancel, j times j become minus 1. Now, what it means is that now the wave, this one become like this. Then now the wave not only propagate with a propagation constant with a real part beta, which is the propagation. Now this real part become equal. Because wavelength is a real number, right? Wavelength cannot be complex. So beta equals 2 pi over lambda. But the wave also get attenuated as it propagates because of e minus alpha z. Okay, so the wave is not constant anymore, but the wave is attenuated. So that is the concept. Alright? Yeah, this is what you say here. Okay, because of this, everything else works. Everything else works the same. Okay? Now I will upload this one on the IBLE. So not to worry. Okay, let's come to where is it now? Okay, lost. Okay, lossy media. Sorry, my code is not very good today. Alright, going with me, lossy medium. Lossy medium, the conduction current equal to sigma E comes into effect. Okay, comes into effect. Alright, all this is never mind, but it's just history. So you just have to add sigma E in here. Have to add sigma E in here. Okay, have to add sigma E here. Originally is this one j omega epsilon E. Originally is j omega epsilon E, now sigma E in here. So this now become epsilon C. Now, so epsilon C equal to epsilon plus sigma over j omega is equal to this. Nobody asked me why this is minus, why this is plus, right? Because 1 over j is equal to minus j. Okay? Now, so all these definitions actually serve to confuse people. Okay, serve to confuse people, but when you read book, there are so many definitions. Okay, so epsilon C is equal to this. Okay, so epsilon C is equal to epsilon plus sigma over j omega, which is equal to sigma minus j omega. Okay, this is the original, which is also equal to epsilon prime plus j epsilon double prime. Okay, I don't know why they need so many definitions, but never mind. So epsilon prime is the epsilon, actually epsilon double prime is the sigma over omega. So you see that epsilon prime is actually epsilon double prime is sigma over omega. Alright? Okay, and the ratio between epsilon prime and epsilon sorry, the ratio between epsilon double prime and epsilon prime is what we call the loss tangent. You see, so many definitions. Okay, and loss tangents greater, very much greater than 1 is called a good conductor. Loss tangent very much smaller than 1 is a good dielectric. But be careful, okay, you note it carefully that for the same material, the loss tangent is a function of frequency because of the gamma of omega delta. So at some frequency, a material may behave like a conductor. At another frequency, the material may behave like a dielectric. Because this is the ratio. What is this ratio? What is this ratio between epsilon prime, double prime, and epsilon prime? By the way, can somebody tell me what does it mean? This is actually the ratio between the conduction current and displacement current. This is the ratio between the conduction current and displacement current, because you see that this one here comes from the conduction current. This one here comes from the conduction current. This one here comes from the displacement current. So the loss tangent is actually the ratio between your conduction current and displacement current, right? So of course, conduction current greater than displacement current is a good conductor. Conduction current less than displacement current, of course, is a good dielectric. Obviously, right? So this is actually a ratio between the conduction current and displacement current as well. Alright? And of course, epsilon C, some people can also define as epsilon naught, epsilon RC. Okay? I say again, many definitions. But we still have to introduce, because a lot of books using all these definitions. If we don't introduce when you read book, you don't know what it means. Okay, so epsilon RC is actually epsilon C divided by epsilon naught. Okay, epsilon RC is actually epsilon C divided by epsilon naught. So it's actually this whole thing divided by epsilon naught. Okay, this whole thing divided by epsilon naught. Okay, so it's equal to epsilon R minus J sigma over omega epsilon naught. Alright, that's all. Definitions. Okay, as I say, I still have to introduce them to you. Okay, now K, epsilon is being replaced by epsilon C. So now we call the K as Kc now. Okay, K naught designate for K in free space, loss in free space. K is designated for lossy medium. Kc is designated for loss. K is for lossless medium, Kc is lossy medium. Alright? Now, and Kc equal to beta minus J alpha. You ask me why Kc is not equal to beta plus J alpha. It will not be. Okay, it will not be, because for any real material, when you put all the number in, okay, you can always find that K is equal to the real, positive real number minus J alpha. Alpha is also a positive real number. Alright, why Kc must be equal to this? Why Kc cannot be equal to this? Why Kc cannot be equal to? Why Kc cannot be equal to? Somebody tell me why. Very simple, alright, very simple. Because if this is a minus over here, this one becomes plus. Okay? If beta is minus here, this will become plus. Obviously cannot. Because our forward propagating wave is E minus J beta Z. If E plus J beta Z, it becomes a backward propagating wave. Cannot be. Alright? And this thing cannot be This thing cannot be. And this thing cannot be positive. Why? Because if this thing is positive, this is positive here, this is positive here. So that means the wave, when they propagate, the magnitude gets stronger and stronger and stronger and stronger. Where the energy comes from? Wow, like that, if we can get energy out of nothing, then we don't have energy crisis in this world already. Okay, so the wave propagate, it can only, the strength can only be reduced, cannot be enhanced. Okay, unless there's something done. So when you solve the equations, okay, when you solve the equation, you find that it always becomes positive number, negative sign here. If you got anything else, check your calculator again. Alright, your calculator will be wrong. Okay, you cannot get anything else but beta minus j alpha. Alright, okay, the value of alpha and beta can be calculated using your calculator to directly calculate the square root of a complex number. Can your calculator do square root of a complex number? Change complex number, the polar form, and calculate square root, use the slide table in slide 16. Now, okay, this one you know, yeah, this one is here. Okay. Now, at this point here, I want to pause a bit. The complex number. Okay. Can somebody how to do, let's say 3 plus j4? Tell me how to do 3 plus j4. Convert it into polar form first. Okay? So convert it into polar form, we put the square root here. Now the magnitude of this is 3 squared plus 4 squared is equal to 5, right? E, J, up 10 minus 4 over 3. Am I correct? Okay? Now I call this, let's say I call this A, E, J, theta. Alright? Now, the square root, how to take the square root? The square root is equal to the square root of A, E, J, theta divided by 2. Okay, for the angle is divided by 2. Alright, so this is how to take the square root. Okay, if your calculator cannot do square root of A plus JB, if your calculator cannot do like something like this, if your calculator can do this, okay lah, good for you. If your calculator cannot do, okay, then convert it into polar form and convert, remember, a lot of students make these mistakes, okay? A lot of students make this mistake. This one, the magnitude here should be square root of 5. Correct or not? Because this is 5. Okay, a lot of students just put it as 5. Because they forget they're going to take one square root and another square root. Okay, because 5 is equal to square root of 3 squared plus 4 squared. So they take one square root and then they don't forget to take another square root. Okay, so these are common mistakes. Okay, don't make this common mistake. And another mistake is, of course, forget to divide by 2 for the base. Alright, and you make so many mistakes, of course, the answer is will be way out. Alright, consider the wave propagation in the plus z directions. This will become like this. We have said that already. Alright. Okay, the general form. Okay, the general form is okay. So the general form is all the same. You can see that. You can see it's the same. You see this equation is the same. This equation is the same. This is the same. This is the same. Zeta becomes zeta c. That's all. This is the same. Okay, you just replace k by kc, zeta by zeta c, epsilon by epsilon c. So it becomes like this. Epsilon becomes epsilon c, k becomes kc, zeta becomes zeta c, everything in a subscript there. So that's all. This equation is still the same. This equation is still the same. This equation is still the same. This equation, remember, because this is theta c, so that means this one has a phase angle. So this is a complex number now. Okay. So this is complex number. This is complex number. This is complex number. All are complex number. And this is how the wave will looks like. The magnitude will decay. All right. The magnitude will decay. Okay. Now, there is a minor things that you have to be careful during the conversions. Right? So now it is now become like this. Like this, right? And remember just now when we say that this is E let's put it simply lah, don't have to write so general direction. So we just assume that it is in the K, in the Z directions. So my E so my H become what? My H become E naught divided by theta. So E naught divided by theta cosine okay? Now, can you see that? Electric field, the phasor form, okay, has a polarization E, magnitude E naught, Ej omega t, Ej phi, E minus j k z, assuming that it is propagating in the z directions only, alright, positive z direction. So the instantaneous form convert it down, E is here, E naught is here. This whole thing become a cosine. Alright? Now, H, what is the difference between H? The difference between H and E is just that these three things are orthogonal. E, H, K are orthogonal, that's all. So the polarization is now H. Okay? And the magnitude, you can see that it's E naught divided by zeta, and cosine term is still the same. Phasor, still the same. H is equal to H here, magnitude E naught divided by zeta, then Ej omega t, Ej phi, Ej minus kz. No problem. Okay? This is no problem. Now, what happened for this one? Now my ER is equal to E naught, Ej omega t, Ej phi, E minus j beta, E minus alpha z. Am I correct? Because now this K now is equal to beta minus j alpha. So I put this in. So right? The rest the same. Okay. Then, what is my instantaneous form? E minus alpha z cosine omega t minus, beta z plus phi. Convert from phasor to instantaneous form. You take all the phasor, the real part of the phasor. Phasor is equal to cosine theta plus j sine theta. So you take the real part of it become cosine. Alright? But the E minus alpha z is not part of the phasor because this is real. This is not an imaginary number or a complex number. So it should retain outside here. So it retain outside here. That's all. Now, what happened to h then? What happened to h? So h is equal to h, my E naught, now, my E naught divided by zeta c. Zeta c has a magnitude Ej theta zeta. Correct or not? Because now this divided by zeta c, you got to put it in here. Okay, so I have my okay. Then I have E j omega t E j phi E minus j beta z E minus alpha z. Am I correct? So everything else the same. But then if you put it down here properly, it becomes E naught zeta c. Now this one you have to bring out, become E minus j theta zeta E j omega t E j phi E minus j beta z E minus alpha z. Correct? Everybody alright? Follow me? Follow? No? Where did you lost? Huh? Okay, let me finish it. Then we'll start over again, alright? Now, so how to write the instantaneous form now? Remember, all the phase angle must go into the cosine. So this is magnitude. This is magnitude. And everything else go into the cosine. There you go. Okay, that's what the next slide is all about. Alright, one more time, alright? I'll start one more time. I'll try to organize this one and put it in the slides for you, alright? This equation still hold. Okay, polarization still hold. Now polarization, this is a position vector. Okay, position vector cannot be a complex number. Okay, position vector is a real vector. So this is a real vector, this is a real vector, EHK is a real vector. Now, the phasor form for E is equal to polarizations, magnitude, Ej omega t, Ej phi, phi is a phase angle, at time equal to t0 and at the origins. Okay, and E minus jkz, assuming that it is propagating in the z direction. Okay, we don't want it too general, right? Too general confuse people even more. So the instantaneous form. Now, what is instantaneous form? Instantaneous form is, you look at all this thing here, look at all the exponential terms. If all the exponential terms have a j here, have a j here, have a j here, all the exponential that have a j, that means you must put inside a cosine term. So, rt is equal to E E naught. See, everything have a J there, so all inside the cosine. Cosine omega t minus kz plus phi. Then H then, okay, H, you make use of these equations and you do the phasor forms. E become H, polarizations. E naught got to divide by zeta, so E naught divided by zeta. Zeta is real, so just divide by zeta. Ej omega t, Ej phi, Ej minus j kz, everything is the same. So from here to here, just simply divide by zeta. And when convert it back out, this is the same, this is the same. These have all have j here. All have j here. And all the terms that have j, you're going to put inside the cosine term. So cosine omega t minus beta z plus phi. Alright? Now, wow, bad man. All these things will be immortalized in video every time I'm just sneezing and sneezing and sneezing away. Very bad. Okay. Now for the lossy. Lossy now my k equal to beta minus j alpha. Okay. Remember? So my ER become E from here to here. Here I just go from here to here. Okay. I just go from here. Go from here to here. Polarization E is the same, E naught is the same, Ej omega t is the same, Ej phi is the same. So I put k equal to beta minus j alpha inside here. I get E minus j beta z minus alpha z. That's all. Okay? Now, convert this one to instantaneous. Remember, those things that with j go inside the cosine. Those things that without the j, the exponential without the j, goes to the, cannot go put inside the cosine. So E is here, E naught is here, this thing is here, because it cannot go into the cosine, and all this going to here, cosine. Is it alright? Okay? Is it alright? Okay, yeah? Everybody alright, huh? Now then H one. H, okay. Now the same thing. E become H here, the polarization become H here. Now my E naught, down here my E naught divided by zeta, but now my E naught divided by zeta c. Okay, and zeta c is complex. Okay, so zeta c is complex. So zeta c has a magnitude and has a phase angle. Okay, then the rest the same. Ej omega t, Ej phi, E minus j beta z, E minus j alpha z is the same. Now, and of course, then I just write like this. J theta, Ej theta is equal to E minus j theta. Right now. Because E1 over Ej theta is equal to E minus j theta. Alright, this is okay, right? So I just put it out here, bring this out here, E minus j theta, Ej omega t, Ej phi, this one, the same. So same thing, everything with the j terms, all exponential with the j terms got to go into cosine, otherwise you leave it outside. H is here, E naught over zeta c magnitude is here, E minus alpha z is here, the rest omega t minus z plus y. Okay. So what does it mean? What does this mean? It means that, okay, just now we say that what is the difference between lossless and lossy is, first of all, the wave is attenuating while propagating. Okay, then we see another phenomenon now. You see that the E and H here, they are in phase. They are exactly at the same cosine term, they are in phase. But for lossy medium, the E and H is out of phase by theta n, theta zeta. It's out of phase by theta zeta, the phase angle of the intrinsic impedance. Alright? So that's about all. Alright? So that's about all. That's what it said here. case example. Wow, we still have a bit, man. Okay, I think we'll do the two special cases, and then we will do the class test and call it a day. Okay, everybody understand what I said so far? Alright. Now, once again, okay, the two special cases. Hey, why is this one like this? Just now, what we say that epsilon double prime, epsilon prime is equal to sigma over omega over epsilon. Alright, whether it's big, very much smaller than 1 or very much bigger than 1. Why this one is different? Hey, the same, alright? Sigma over omega over epsilon is the same as sigma over omega epsilon. Alright, they are the same. Alright? Don't come and tell me, hey, how come this one definition and this definition different? Same definitions. Alright? So is greater than 1 is a great conductor, is less than 1 is a low loss dielectric. Now, when the loss tangent is very much greater than 1, okay, we can simplify the complex number. Okay, k is a complex value, remember. What is the value k now? K is equal to omega square root of mu epsilon. So now it's equal to omega square root of mu epsilon minus j sigma over omega. So it's a complex number, correct? It's a complex number here. Now, if this is very much greater than 1, okay, then k, which is equal to beta minus j alpha, it ends up that beta is approximately equal to alpha is approximately equal to this value, square root of pi f mu sigma. Alright. I'm not sure whether these equations will be given in exams, so I better check. So if it's not given in exam, this equation and this equation, you better copy it down, alright? I will check for you whether these are inside there. And zeta c, which is the characteristic or intrinsic impedance of the lossy media, is equal to square root of 2 and alpha over sigma. Alpha is this alpha here. Sigma is a conductivity. And the phase angle, just now this phase angle zeta c here, this phase angle zeta c here is exactly equal to pi by 4. Okay, exactly equal to pi by 4. Alright? So, and the velocity of propagations, the phase velocity, okay, remember the phase velocity, initially we define as omega over k, but now k is a complex number, and the velocity of propagation cannot be complex, okay, never heard of a complex velocity of propagation. This is defined omega over beta, which is equal to square root of 2 omega over mu sigma, okay, this is another equation that you need. And the wavelength, okay, this is another equation that you need, defined as 2 pi over beta, not 2 pi over k, because k is complex now, so we take only the real part. Okay, this is the wavelength. Okay, these two equations you need as well. Now, in a good conductor, because of attenuation, okay, this is so we call the skin depth. Okay, skin depth is an engineering tool. Okay, see, skin depth is not actually anything that is mathematically fantastic. They say that in a good conductor, the wave will attenuate. Okay, the wave will attenuate. And this thing will attenuate all the way up to infinity. I mean, every time if you want to integrate, we integrate up to infinity and do an engineer don't care. We don't care with such thing. So we say that by the time at the skin depth delta, okay, delta means that, remember that attenuation is E minus alpha z. Okay, when E minus alpha delta is equal to E to the power of minus 1, or delta is equal to 1 over alpha. Okay, delta equal to 1 over alpha. We say that, okay, at this point here, at the delta, the decay E minus alpha z is equal to minus 1. We say that all the energy will be lost. Okay, this one negligible. we say that all the energy will focus in here. The rest are negligible. Okay, engineers. All right, we take shortcut. This is what we call skin depth. Now, this is something very interesting now. Probably something you never consider, you never worried before. Is that, for instance, okay, we have done. Can I clear this? Okay. Yeah. Okay. The resistance of a resistor, R is equal to L over sigma A. Right? You know that? Okay. Let's say per unit length, I give an example, then this is equal to L over sigma pi A squared, right? This is A, this is the cross sections of the current flow. So at DC, give you an example here, if the R is equal to 1 mm, the radius of the wire is 1 mm, okay, and the length is 1 meter, for 1 meter length of the wire, 1 mm radius cable, the resistance is 5.5 milliohm. Alright. But however, at high frequency, remember, when the wave propagates inside there, now it has a lossy material, and in lossy material it has a skin depth. So at a certain frequency, I don't know which frequency, let's say at 1 megahertz, let's say at 1 megahertz, the wave or the current will only, instead of distributed uniformly across the cross section, only distributed in here. There is zero current here, and this is my skin depth. And the skin depth gets thinner and thinner and thinner as frequency goes up. You can see that when frequency go up, alpha go up, frequency go up, alpha go up, and del, the skin depth is equal to 1 over alpha. Okay, and skin depth is equal, del is equal to 1 over alpha. So when frequency go up, alpha go up, skin depth goes down. So this one becomes thinner and thinner. So now my area is L over sigma. What is my area? The area is 2 pi r times del. This is the area of this ring over here. Okay, so I do it this way, 2 pi r times del. At 1 megahertz for the same piece of wire, the resistance is 41 milliohms. It's 8 times more than what you have calculated. And at 1 gigahertz, can you imagine how much more that it's going to become? So when you use wire at high frequency, a lot of people who doesn't know about EM will always underestimate the attenuations. Okay, always underestimate the attenuations. You have to calculate. And for all of you, from your background, you know what is printed circuit, right? You know what is printed circuit, and you know that this is the printed circuit tray, this is the ground plane, right? Okay. Now, high frequency, this thing here, the current will not flow throughout the whole trace. The current will actually flow only on a very thin layer of this one. And because of this effect, heat dissipations become more difficult, resistance become much higher. And in order to reduce all this effect, a lot of people do a gold plating. You see, businessmen are businessmen. Why Why for nothing they gold plate the whole thing? They cost money. Gold plate, although it's very thin. The reason is so that the current can flow on the gold plate, and since the gold plate has a better conductivity, heat conductivity as well as other conductivity, this one becomes heat loss. Heat dissipation is better, and also the resistance is lower. And that's why they don't coat it properly. All right. Okay. Okay. These are some equations. As you can see that the skin depth actually changes for copper quite a bit. 60 Hz is 8.5 millimeter. 1 megahertz is 66 micrometer. At 30 gigahertz, it is only 0.4 micrometer. Very, very thin. And that actually gives you one good thing, but there's one good thing about it is that if you want to shield, you see, if you want to shield, let's say you want to have a shielded room. Okay, you want to shield shielded rooms. If the attenuation is e to the power -1, you need about a couple of millimeter. But at such a high frequency, you need only a micrometer. So that means your shielded box, if you want to shield a box equipment from radiating, okay, to meet FCC requirement, or you want to shield a box or shield a room to prevent any interference from inside, at high frequency it's very easy. Right? It's just a thin layer of copper sheets, and everything is done. So, but of course the reverse side is that at power frequency it becomes very difficult. We're not going to discuss that. Discuss that at 501. So I'll do it with you 501. All right. 501 is called electromagnetic conductivity, compatibility. Okay. Okay. So these are some of the skin depths of the common material at different frequency. All right. Okay. And that also brought up another anomaly down here is that, okay, why you cannot have underwater radio communications, or underwater radio electrical communication must be via wire. By wire. Because you see, you can look at it very easily. At even 1 megahertz, the skin depth is 0.25 meters. So a couple of meters away, you actually cannot receive anything. How to use radio communications underwater? Iron connection must be by cable, okay? Otherwise, must be by sonic. Okay, and submarine. So submarine, how to communicate? Okay, submarines, they only communicate when they come. This is the water surface. Only when they come to the water surface and stick the antenna up to the water surface. This is when they communicate with the satellite. And that is when they are most vulnerable, because they stick the antenna up, they are detectable. Right below here, nobody can know where they are, but if come out here, they are detectable. So it's the most vulnerable. So normally, how do they do is that Singapore don't have it, because only US, Russia, this big company have a big country have. They have a so-called antenna farm for submarine communications. The antenna farm is actually in terms of tens over kilometers. The antenna is 10 over kilometers long. Okay, so they are actually radiating at probably 5 hertz or whatever hertz. So at this hertz, you cannot, you guys know modulation, right? You cannot modulate anything. You need 5 gigahertz to modulate it. 5 hertz, you cannot modulate it. So what they do is Morse code. They do it by Morse code. So this thing can go underwater, communicate, because such a low frequency, the skin depth is much lower, they propagate. So when the submarine here, they are Morse code, okay, is their code, so they emerge out, okay, so they then receive their instruction, and then they go back down. That's the only way to do it. Okay, a lot of things is limited by the nature. This type of thing is not, because technology cannot overcome. This is nature. Okay, nature thing cannot overcome. Alright, so when the sigma equal to infinity, skin depth equal to 0. Alright, low loss dielectric, let me finish this part, alright? Low loss dielectrics, when this one loss tangent curve is much smaller than 1, you expand this one by using binomial theorem. Okay, I hope you will like it. Okay, 1 plus x when x smaller than 1 equals to this whole thing. Alright? So we expand it using binomial theorem and keep the first and second term, you throw away the higher order term, that's what you have here. So k equals to beta minus j alpha. So this is alpha, this is beta. And remember, the beta has the same form as the lossless medium. So beta has the same form for k as a lossless medium, but it has an alpha. Alright, it has alpha here. Alright, so these are the equations. Okay, the equations for velocity is still the same. Okay, equation for velocity is still the same. The equation for wavelength is still the same. The equation for zeta is still the same. The only difference is that now it has an alpha and it is still there. Alright. Okay. I remember this equation is given in exam. If I this particular chart is given in exam, let me check again. Alright. Okay, so for any medium, lossless medium, low loss medium, good conductor. Alright, so this all the formulas are here. And I do remember this table is given in exam, so not to worry. Okay. As I say, I will double check. Actually very simple. Anyone of you just call up one of the past year paper, you see whether it's inside there or not already. Alright, any questions, ladies and gentlemen? What I'm going to do is going to do the class test now. Let me take a rest. And Friday we will finish off the example. And we will do the tutorial. Have we done tutorial 5 yet? Not yet, right? Okay, so Friday we will finish it off and we will do tutorial 5, and then next week we will do tutorial 6. Okay? Okay. Okay.
Wow.
What's that? Hey, you see, if you have more questions, that means you got better grade. You get 3 out of 4, 75 marks.
Wow.
You know, if you 2 questions, 1 out of 2 is only 15 marks. So more
Or
questions.
if you one question don't know how to do, you all questions know how to do, you know.
Plus, 有一张。